Welcome to this exploration of one of the most profound shifts in our understanding of the universe, the difference between classical physics and quantum physics. For centuries, classical physics explained the world around us. From the motion of planets to the trajectory of a thrown ball, the laws formulated by Newton, Maxwell, and others gave us a framework to predict and understand the physical world. But in the 20th century, scientists discovered phenomena that classical physics could not explain, leading to the birth of quantum physics, a theory that defies our everyday intuition and challenges the way we think about reality itself. Classical physics operates on the principle of determinism. If you know the initial conditions of a system, such as the position and velocity of an object, you can predict its future behavior with certainty. This approach works perfectly for large objects, like cars, planets, or pendulums. Classical physics also assumes that energy, matter, space, and time are continuous and measurable to any desired precision. Forces act on objects, objects respond in predictable ways, and cause and effect are clear. Quantum physics, however, operates in a world that is fundamentally different. At the scale of atoms and subatomic particles, the rules of classical physics break down. Particles can exist in multiple states at once, a phenomenon called superposition. A single electron, for example, does not occupy a single location until it is measured. Until that moment, it exists as a probability cloud, a spread of potential positions where it might be found. This is a radical departure from the deterministic world of classical mechanics, where an object always has a definite position and velocity. Another key difference is the concept of uncertainty, formalized by Werner Heisenberg in the uncertainty principle. In the quantum realm, it is impossible to know certain pairs of properties, like position and momentum, with absolute precision. The more precisely you measure one property, the less precisely you can know the other. This is not a limitation of measurement tools, but a fundamental property of nature. In classical physics, such limitations simply do not exist. Entanglement is another phenomenon that has no counterpart in classical physics. When particles become entangled, the state of one particle is directly linked to the state of another, no matter the distance separating them. Changing one particle instantaneously affects the other, in ways that seem to defy the constraints of space and time. Einstein famously called this spooky action at a distance, because it challenged the classical notion that nothing can travel faster than light. Quantum physics also introduces the concept of wave-particle duality. Particles such as electrons and photons can behave both as particles and as waves, depending on how we observe them. Light, which classical physics described as a continuous electromagnetic wave, also exhibits particle-like properties, appearing in discrete packets called photons. Similarly, electrons, once thought to be simple particles, can create interference patterns like waves when not measured directly. This duality is completely foreign to classical physics, where waves and particles are distinct entities. Despite these differences, quantum physics does not invalidate classical physics. Instead, classical physics emerges as an approximation of quantum physics in the macroscopic world. The deterministic laws we observe in everyday life are simply the result of averaging out the probabilistic behavior of countless quantum particles. Classical physics works extremely well for most practical purposes, from engineering bridges to sending rockets to the moon, but it fails at the microscopic scale, where quantum effects dominate. Quantum physics has also led to remarkable technological advances. Devices like lasers, semiconductors, MRI machines, and even smartphones rely on quantum principles. Understanding quantum physics allows us to manipulate atoms and electrons in ways unimaginable in the classical framework, giving rise to new fields like quantum computing and quantum cryptography. These technologies exploit superposition, entanglement, and other quantum phenomena to perform tasks far beyond the reach of classical systems. The philosophical implications of quantum physics are equally profound. Classical physics presented a universe governed by absolute laws and predictable outcomes, reinforcing the idea of an objective reality. Quantum physics challenges that certainty, suggesting that at a fundamental level, reality is probabilistic, and observation plays an active role in shaping the outcome of events. Questions about the nature of reality, causality, and the limits of human knowledge arise naturally from the quantum perspective, inspiring debate and reflection that continues to this day. In summary, classical physics and quantum physics describe the universe on vastly different scales. Classical physics governs the macroscopic world with determinism, continuity, and predictability. Quantum physics governs the microscopic world with uncertainty, probability, and phenomena that defy classical intuition. Together, they provide a more complete understanding of the universe, each excelling where the other fails, and opening doors to technologies and insights that were once thought impossible. Exploring the differences between classical and quantum physics not only deepens our understanding of the universe but also reminds us that reality is far more complex and astonishing than our everyday experience suggests. As we continue to probe the quantum world, we may discover even stranger and more powerful truths about the nature of existence. Forever expanding the boundaries of human knowledge, thank you for joining this exploration of classical versus quantum physics. The journey from Newton to quantum mechanics is one of the most exciting chapters in the history of science, and it continues to shape our world in ways we are only beginning to understand.